we're going to calculate now the matrix associated to general linear transformations. For that, we're going to use all what we know of calculating matrices associated to transformations in Rn, as well as the isomorphism between any vector space and Rn that we saw previously. So we have basis B of the first space here and a basis C of the second space here. So the space B is dimension n and the space W is dimension m. So we're going to construct now the matrix of T relative to these bases, to the bases B and C. This is going to be the notation, so we put the transformation T, and so the first of the bases to the basis of the second space. And so this matrix is a matrix whose columns are going to be the coordinates of the images by T of the vectors in the base B relative to C. All of these words have a very particular meaning, and let's analyze one by one. So first you need to do the images by T of the vectors of the base B. So what does it mean? We take the vectors in the base B and we do the images by T. So we transform them, the images of U1, the images of U2, etc., until all the images are calculated. But we are not going to use these vectors as they are. According to this, we need to find the coordinates relative to C. So these vectors are not going to be just as they are, but we need to write it in this base, in the base of the second space. Next thing that we have to do, so we have to write these vectors now in the base of the second space. So these coordinates, those coordinates now, when it's written in the other base, are the ones that are going to be the columns of this matrix. Okay, so this is then the way to calculate this matrix, and once that we have this matrix calculated, we can use it to calculate the image of any vector. So we put here the image in the first base, we multiply by this matrix, and then the result should be the image of the vector in the base C. Let's see an example. Just one more thing before, just about notations. When the base is the same one, we will normally say the matrix for T in base B. So we write the base just once if it happens that the two spaces are the same and have the same base. But this is the formula more general for any spaces of any dimensions with any bases B and C. Okay, so let's see how this thing works in an example. Let's calculate in this example the matrix for the transformation. When I write nothing here, means that it's in the standard basis, right? So I will mean the standard basis of this polynomial space and the standard basis of this polynomial space. That we can just write this like this, with nothing that means the standard basis. But have in mind that actually this is B and this is C in our formula, right? When it's a standard basis, everything is going to be easier. But this formula for any B and any C, in this case, the base B is the standard basis of P1 and the base C is the standard basis of P2, which we can actually write in the standard basis of the first one. We know that is 1x, and the standard basis of P2 is 1x, x squared. And so In order to calculate this matrix, we need to find the image by T of each of the elements of the first base, right? So let's calculate the image, and we will calculate depending on the transformation. In this case, this transformation does this. Take the first one and multiply it by x. So in this case will be x, and this bx plus bx squared, so in this case is 0, will be 0. So here, so each of the vector here is a plus bx, right? And we'll get transformed in ax plus bx squared. So in this case, this is 0 plus 1x. So we'll get transformed in 0x plus 1x squared. So that's why it gets transformed just in x squared. Okay, so x, we express it in the base of the second space, that in this case will be 0 times 1 plus 1 times x plus 0 times x squared. So the coordinates of this transformation here, I mean, when we go toward the isomorphism, right? I mean, in terms of coordinates, this will be 0, 1, 0. So that will be the coordinates in the base C. We do the same thing for this one, that is 0 times 1 plus 0 times x plus 1 times x squared. So the coordinates are going to be 0, 0, 1 in the base C. So by calculating these two coordinates here, we have the actual columns now of our matrix. So the matrix that we wanted to calculate, the matrix BC, that in this case is just the same thing that this, so because are both the standard bases, it's just writing these vectors as columns. So 0, 1, 0, and now this other one as columns, 0, 0, 1. So this is the matrix that we were looking for. And now, following our formula, so we have that by multiplying this vector, this matrix by the vector, we are going to get here the transformed one. So we know that if we multiply 0, 0, 1, 0, 0, 1, if we multiply now by any vector in the base B, so a vector in the base B, the a plus bx will be just ab. These are the coordinates. And so when we do the multiplication here, this times this, 0 plus 0 is 0, this times this, a plus 0 is a, and this times this, 0 plus b is b. So this is the transform vector here. So that will be the transform of a vector AB in the base C. This was in the base B, and this is in base C. These are all the standard bases, but so in general, that is what will it be. If we review here our diagram, so I remind you the diagram that we have in the other page. So the diagram in this case, we will have the vector space V, that in this case is P1, and so the vector space W, that is P2. Here we have the actual transformation, and so we go here with the isomorphism to R2, and here with the isomorphism to R3. And here, from here to here, we are going to have actually this matrix. So this matrix here, the matrix 0, 0, will allow now to travel around all this diagram in any way we want. So for instance, here, if we start with a polynomial a plus bx, we transform this one in the coordinates in R2. The coordinates are going to be just AB. And now, if we multiply by this matrix, so we're going to have here, as we did before, this multiplied by AB, that we obtain the vector 0, A, B. So we obtain here the vector 0, A, B. in the base C, but these are the coordinates. So if we want to complete this, where this one comes from here, if we want to complete this, where this one comes from here, what is the polynomial that we should put here? Well, in order to get 0ab, the polynomial should be 0 times 1 plus a times x plus b times x squared. So by doing the operations here, we see that this polynomial is nothing but ax plus bx squared. That is exactly the transformation that we have, that t applied to this is equal to this one here. Well, let's find in this example the matrix associated to t in the base B, where t is this transformations in the vector spaces of polynomials, such that take any polynomial of degree 2 like this and transform it in this. And the base is the base 1, x plus 1, and x squared minus 1. Okay, so following our previous process, we are going to start by transforming, finding the image by t of the vectors in the base B. So I'm going to transform the first vector. This is 1. I transform it following the definition here of the transformation. This polynomial 1 is a polynomial 1 plus 0x plus 0x squared, right? According with this formula, will be transformed in just 0, right? Will be transformed just in 1. All the remaining is 0. So the transformation of the polynomial 1 is 1. So now let's go to that means that the image of the vector 1, which is the polynomial 1 in this case, is the vector or polynomial 1 in the second space. Now let's go to the second vector in the base, the polynomial x plus 1, and let's transform it. So the polynomial x plus 1 is 1 plus x, right? Transforming in here will be a, that in this case is 1, plus b, that in this case is also 1, times x minus 1, and the remaining will be 0, because c is 0 in the original one. So the transformation is 1 plus x minus 1, in other words, x. So we got that the image of the polynomial x plus 1 by this transformation is then x. Now let's transform the last element in the base, which is the polynomial x squared minus 1. So let's transform then x squared minus 1, which is minus 1, plus x squared, right? So that will mean here a, which is minus 1, plus b, that is 0, right? There is no term in x, all this part will be 0, and then plus c is 1, times x minus 1 squared. So this is minus 1 plus x squared minus 2x plus 1. So in other words, 1 minus 1 cancel, x squared minus 2x. Okay, we got the image then of the transformation of each of the vectors. So if we remember here our definition, so we have here this part so far. We have the images by t of the vectors of B. Now we need to calculate the coordinates of those relative to the base C. Then the coordinates of these vectors in this base. So this is going to be equal to, and let's find out what are the coordinates. Should be certain A times 1 plus B times the other one plus C times the other one. And let's find out the coordinates. So when we solve this system here, we see that it's going to be actually the same operations for the other one. Let's do these operations separately. So this is a plus bx plus b, doing distributive here. And so we continue distributive also here. And so this is plus cx squared minus c. Let's combine like terms, these three things together, a plus b minus c. And now determine x plus bx and then plus cx squared. So that is then the algebra done in here. And so this equation that we got here have to be equal to the polynomial 1. That means that we got this system of equations. A plus b minus c equals 1, b equals 0, and c equals 0, right? Because there are all zeros there, the terms in x and x squared. Solving this system, so we have that a is equal 1, b is equal 0, and c is equal 0. So these are then the a, b, and c that we were looking for. So this polynomial then have coordinates in the base b 1, 0, 0. So these are the coefficients that we have to put here in the base b. Well, in the same way, we find the coefficients for each of the other polynomials. So we need to multiply a by something plus b, etc. We do the same thing. The system that we are going to obtain is going to be the same. But now we want this to be equal to this polynomial, that is x. So this should be 0, this should be 1, and this should be 0. Solving this system of equations, we get here that a is actually equals to minus 1, b equals 1, and c equals 0. So these are then the components of this vector, the vector x in the base b. Minus 1, 1, 0. In the same way, we want this certain a times 1 plus b times x plus 1, etc. And so we are going to get exactly the same system, but now it's going to be equal to this polynomial, right? So the number is going to be 0, b is going to be minus 2, and c is going to be equal 1. So when we solve for this, we get here that a is equal to 3, b is equal to minus 2, and c is equal 1. So these are going to be the components of this vector then in base b. So are going to be 3, minus 2, and 1. Okay, so we got then all the components of the vectors in the base b. So by having that, we have now the actual matrix that we were looking for. So the matrix associated to b is going to be just the matrix that have these vectors as columns. As we were saying here, the columns are the coordinates of the images by t of the vectors relative to the base c. And so this is going to be then the first vector here, which is 1, 0, 0. The second one, which is minus 1, 1, 0. And the third one, which is 3, minus 2, 1. So this is the matrix of the system in the base B. And we can state now, having this matrix, that if we multiply any vector in the base B, we are going to obtain then the result in the base B2. So in this case, let's for instance consider some vector here to transform. So a vector is going to mean any polynomial of degree less or equal than 2. So let's say b could be the polynomial, let's say 3 plus x plus 5x squared. Okay, so this is the polynomial given in the standard basis. This is the polynomial b. So now, if we express this polynomial in the base b and multiply by this matrix, we are going to find the result in the base b too. So let's express first this polynomial in the base b. This is something that you already know how to do. So that will be to do again the same, but in this case with this polynomial. This polynomial, how would be expressed in the base b? Well, we have to find an a times polynomial 1, b times polynomial x plus 1, plus c times polynomial x minus 1. And we have to find how much is a, b, and c. We have already done this system several times, so we know that the system is a plus b minus c equals the coefficient with number, which is 3, the other one is just b, and the last one is just c. So b should be equal to 1, and c should be equal to 5 in this case. So solving this, a is equal to 3 minus 1 plus 5, that makes 3 equal 7. And so to express the vector b in this space is to write it as the vector. Let's write this as the vector, then 7, 1, 5. So that will be the vector b expressed in the base b. And now if we multiply this vector in base b by this matrix, if we multiply these two things, we will get the image of v in the base b. So we are going to get the image of the vector b. This is a vector also that is a polynomial of degree less or equal than 2. So this vector in the base b is going to be equal to this matrix here multiplied by the vector in base b, which is 7, 1, 5. Let's do the multiplication here. I mean, this times this is going to be 7 minus 1 is 6 plus 15 is 21. And then this times this, that will be 0 plus 1 minus 10. 1 minus 10 is minus 9. And then this times this is 0 plus 0 plus 5, which is 5. Okay, so we have found then this vector is the image of the vector v in the base b. And let's keep this data here in this problem. We're going to come back to this when we study the change of bases. So we're going to generalize now and give a change of bases formula that will allow us to relate the matrix associated to a transformation in certain two bases with a matrix associated to the transformation in any other two bases. And this relation is going to be given by the matrices of change of bases that we have already studied. So let's observe in this diagram how the letters go. So we are saying here, following the arrows, that doing all this is the same thing that doing this in the diagram. So see that you go here from base B prime to B, and then from B to C, and then from C to C prime. At the end of the day, you are going from B prime to C prime. So that is something that you should always check, that all your letters make sense, are consistent. And so this matrix, the matrix associated to the transformation in those bases, is going to be the same that the multiplication of these matrices. So we are going to start by multiplying this matrix that we put here times this one that goes here times this one that goes here. That's the order in which we do composition of functions. So observe that this transformation here is the identity B prime B, and this transformation here is the identity C prime. So this is in general the formula, the multiplication of these three matrices gives that one. This is in general the formula for changes of bases. In the particular cases in which these bases, the ones that we have here, are actually the standard bases, so then we got a formula to calculate the matrix associated to the standard bases in function of the matrix associated to BC, and observe that here and here things get simplified when the bases are the standard. So if you have here, we said that C prime and B prime are going to be the standards. Remember that if you have an arrow like this, C to the standard, what this means is that you will get the bases C and just write in a standard, meaning just write the base directly like that. So when you have standard as the second base, is always just write the matrix right away without having to find out the coordinates in another base. So this one, for instance, will be more complicated because this will be standard to C. Well, that's not that good because we take the bases, the standard bases, but we have to write it in another base. So that will be more complicated. But as we have learned before, this one, even if it's more complicated, can be expressed in terms of the inverse one by just using inverse matrices. So in that way, the formula gets simplified by putting here the first matrix is fine because it's simple, writing the bases as columns. And the second one, even if it's more complicated, we can still write it as the matrix of columns and then calculate the inverse. So this is a formula then to remember. The first matrix here is the matrix associated in the standard. Here is the matrix in any basis you want, B and C, any other basis. And so here the important matrices are the matrices of changes, which are just taking the bases and write them as columns. So you take here the base of W and just write as columns. And here you take the base of B and you write as columns, but then you calculate the inverse matrix in this side. Okay, so let's see an example. So in this case, we have a transformation from R2 to R3, and we know that the image of this vector is this and the image of this vector is this, and we have to calculate the transformation in the standard basis. So first, let's write down B as these bases given here, the base phi minus 1, 1, 0. And let's try to interpret this in terms of then changes of bases. By having the images of these things, so we have a way to calculate right away the matrix associated to T in the base B, because that's the base that we are doing the transformation, and then standard, because these vectors are just in the standard form. So we can put right away that this matrix is just this as vectors, 3 minus 4, 4, and so 1, 3, minus 4. So by reading the data in this way, we have a way to write right away the matrix associated to the transformation from B to the standard. And so how we use this matrix to calculate just the standard one? Well, let's look at our diagram. So in our diagram, we have here R2 and R3, and so we can have here the matrix in the standard, the one that we want to calculate. And so here we change the bases, and here we can go to b, that is the one that we want. So any vector xy, we can write it somehow in the base b. And so here we would like to use the matrix that we just calculate. So we will put here T, B, S. So that means that in here we still calculate the things in the standard base. So meaning that here, this transformation here will be just from the standard to the standard. So X, Y, Z will be just X, Y, Z. So here we will have just the identity, standard, which means just the identity. So the only thing that we need to calculate then is here the identity from the base standard to the base B. So this is the identity in the direction that we don't like, right? Because standard to B is not good. It's where B to a standard, it is good. So then what we're going to do is to calculate the inverse of that. Okay, so let's just use directly our formula. We know this, right? So we're going to use these formulas with the bases that we have. So with our bases, we're going to write that T is equal to PW TBS and PB to the minus 1, where this matrix, I mean the first one here, that will be just the identity from standard to standard. So in this case, this one is just the identity matrix. This one is the one that we just calculate, is this one here. So we can put this one here, 3, 1, minus 4, 3, 4, minus 4. And this other one is the matrix in the first space, and in here will be the inverse of this one. So the identity SB is just PB to the minus 1. I mean the identity BS to the minus 1. And B to S means just to put the elements of the base in the standard form. In other words, just to write them as columns. 5 minus 1, 1, 0, right? So this as a column and this as a column. So that's the matrix PV, and then we need to do to the minus 1. So the inverse of this matrix, let's calculate the inverse by any of the methods. So that would be the matrix 0, minus 1, 1, 5. So we did calculate the inverse. Okay, so this inverse is what we need to write then here. So we're going to multiply by the matrix 0, minus 1, 1, 5. Okay, so let's multiply these three matrices, and the result will be then the matrix in the standard basis. We can actually abbreviate here. We know the multiplying by the identity is just the same as nothing, so we can multiply just these two. Let's do that. So let's multiply this by this. This is 3 times 0 is 0, plus 1 is 1. And then 3, this times this will be 3 times minus 1 is minus 3, plus 5 is 2. And then this times this is 0 plus 3 is 3. This times this is 4 plus 15 is 19. And then this times this will be 0 minus 4 is minus 4, and this times this is minus 4 minus 20, minus 24. Okay, so this then will be the matrix associated to T in the standard basis. There are many checks and many other things that you could keep working in this problem. I mean, if you want just to check that this is correct, you could actually take this matrix and multiply by 5 minus 1 and check that you really get that. The same thing with that. So there are many things that you can keep looking and studying in this problem. And talking about keep working in the problems, let's come back to the other problem that we were looking before. This one. So this problem, I remind you that this was a transformation in the vector spaces of polynomials that is doing this. And we have these bases here, and we were able to calculate the matrix associated to the transformation in that base. That matrix was this one that we have here. Let's check an alternative way to do the same thing. And so that's good to do it with the same problem, just to check that we are getting the same results. So let's see how do we solve this problem. I mean, how do we calculate this matrix that we calculated before, but using now the change of bases. So let's adapt now the indices here to what we want. This is good, the formula for any B, C, B prime, C prime. So let's consider, for instance, B and C, both the standard. So here we will have a matrix that is very easy to calculate. So let's consider then B equals C equal the standard. So then this formula here will be simple, the matrix associated to T in the standard basis. And so here, by putting B and C both equal to the standard, so here we have standard, right? So then this matrix became identity B prime standard. And so here, since C is the standard, here will become identity standard C prime. And this will give us the transformation in the base B prime, C prime. Now, B prime, C prime, actually we want a B, right? So that's the one that we want to calculate. So B prime equal B and C prime equal B. So then applying that, so we will have here the transformation in B. Now both B prime and C prime, we are calling them B. And so then we will have here identity from S to B, T, and here we have identity from B to S. And so now we have here all easy matrices to calculate. This one is just calculating the standard bases and putting the transformation of the standard bases and write it as columns. So this one, because it's B standard, I mean, if the second one is standard, is simple, get the vectors in the base B and write them as columns. The one that will be harder will be this one, right? Because we have to express in base B. So instead of calculating like this, we can write that this is actually the inverse of the identity in the other direction, right? So we can write it like this, and this one will be just the same as this. Okay, so let's write down that, and we are going to have that this is the final formula that we will use. So this matrix, this one, that we have calculated previously by hand, right? But now by changes of bases, this matrix is going to be equal to this. So this formula tells us a way then to calculate this matrix by using a multiplication of three matrices, the three of them very easy to calculate. This one is just the base B, the vectors in B, written as columns. This one is the inverse of that matrix. And this one is transforming the standard bases according to the transformation and write them as columns. So let's do all that. So the matrix associated to the transformation in the base B will be this first matrix, that will be the inverse of that, will be this other matrix here, that is the associated to the transformation in the standard basis, and this other one here, that will be just take the base B and write it in the standard form. Let's start by filling up this one. So let's take the base B, which is this base, and write it in the standard form. I mean, just write it as they are. So the first one is going to be just 1, 0, 0. The second one is 1, 1, 0. And the third one is minus 1, 0, 1. This matrix then is this one. We need to calculate the inverse of that to put in here. Let's do that. Let's calculate the inverse matrix there. So now is the inverse of this one. Use any method of calculation of the inverse and you should obtain 1 minus 1, 1, 0, 1, 0, 0, 0, 1. So this is the inverse of this matrix. And so finally, the last one that we had to complete here is the matrix associated to the transformation in the standard base. So for that, we're going to transform all the vectors in the standard base according to this formula. So let's do that. So let's transform the vector 1, the first vector of the standard base, and then the vector x, and then the vector x squared. So the vector 1, according with this formula, will be equal to 1, and everything else will be 0. So this is just 1. The vector x will be then 0, and then here 1 times x minus 1 times 0, plus 0. And finally, x squared, when we put here x squared, we transform it, we're going to get here 0, 0, and here 1 times x minus 1 squared, that will be x squared minus 2x plus 1. Okay, so that is the transformation then of the vectors in the standard base. So the only thing that we need to do with these vectors is to write them here as columns. So the first one, 1, is going to be just 1, 0, 0. The second one is going to be minus 1, 1, 0. And the third one is going to be 1, minus 2, 1. Okay, so all what remains to do now is to actually multiply these matrices. So let's multiply them. So there are 3 matrices. We have to do 2 at a time. Let's multiply these 2. This times this. We will put the result here, right? So this times this is going to be 1 times 1 is 1, plus 0 plus 0, this is 1. And now this times this is going to be 0. This times this, 0. So this is the result of the multiplication of these 2. And now we still need to multiply by this one in front. So let's multiply by so the result of this multiplication. So we start this times this is going to be 1 times 1 is 1. This times this is 0 minus 1 plus 0 minus 1. And this times this will be 0 plus 2 plus 1 is 3. And we obtain as a result of the multiplication exactly the matrix that we have calculated before. So we have again 2 ways to calculate the matrix associated to a transformation in any basis. So looking at our diagram once more, so we will have here the matrix associated to be here, just the matrix associated in the standard basis. So in this side here will be the identity from the standard to B. If we want to write it in that direction, will be the identity from B to the standard. And so, if we take any polynomial here, for instance, this one in the canonical, so here 3 plus x, I'm doing it with this one, but we'll work with any polynomial at all. So, if we have this polynomial here, expressed in the base B we have calculated before, they have component 7, 1, 5 in the base B. When this vector we actually multiply by this matrix that we calculated before. So that gives us, after the multiplication, gives us the vector 21 minus 9, 5. That should be the vector expressed in the base B here. And now, as we know what means a vector expressed in the base B, right? That means that is 21 multiplied by the first one, minus 9 by the second, 5 by the third. So we can go back and write it back as a polynomial here. So we write it back as a polynomial doing these operations. If you do these operations, 21 times 1 plus, minus 9 times x plus 1, etc., you will get that the polynomial is actually 7 minus 9x plus 5x squared. So then now just check that the transform of this polynomial by this transformation, when you do t of this one, you obtain exactly this polynomial here. That is what we did before. So be sure that you check that everything here makes sense, that you understand all this, and I would advise you to check this with any other polynomial. I mean, you should make up here any polynomial. You should be able to calculate here the bases, to multiply by the matrix, and to go back to here. Then transform the polynomial and everything should coincide. Be sure that you check with at least a couple of more polynomials.